Good morning, friends. I thank my Penn State colleagues, Jim Brakall and Julio Urbina, as well as Chip Cohen, for inviting me to this symposium. In April 2008, I delivered a lecture at the Maxwell Institute of Mathematical Sciences, which is a consortium of the University of Edinburgh and Heriot-Watt University. That year, the 150th anniversary of the first professorial appointment of James Clerk Maxwell was being celebrated, and I had been asked to connect his electromagnetics research to the present day. And that is how the title for today's talk was born, From Maxwell to Nanotechnology. The roadmap for my talk today has 4 stops. I shall commence with an introduction to the seminal contribution of Maxwell to electromagnetics. Then I shall discuss some features of nanotechnology. The third stop is the hot topic of metamaterials, which began in the year 2000. Finally, I shall present sculpture thin films as examples of nano-engineered metamaterials. My aim is to show that an innovation of Maxwell was an acorn that engendered many mighty oaks in the forest of knowledge. A few years ago, I read a travelogue in which Professor John Henry of the University of Edinburgh took the reader on a tour of Edinburgh landmarks associated with prominent physicists. What a wonderful lineup of scientific contributors that city has. From John Napier, the inventor of logarithms, to Peter Higgs, on whose boson the standard model of particle physics squarely rests. But of the 17 illustrious physicists in that travelogue, no name shines brighter than of James Clerk Maxwell. Today, he would have fitted in any major research university with his multidisciplinary research focus. Had Maxwell just worked on the kinetic theory of gases, his name would have been immortal. There is the Maxwell-Boltzmann distribution for the fraction of gas molecules at a specified speed at any given temperature. There is Maxwell's demon that could conceivably violate the second law of thermodynamics by sorting particles by their energy. Had Maxwell just worked on the dynamics of celestial rigid bodies, his name would have been in college-level textbooks for centuries. He theoretically showed the particulate nature of Saturn's rings, confirmed by both Voyager spacecraft in the 1980s. The particles are not stable, however, and will vanish into Saturn in about 300 million years. Had Maxwell just been content to produce the first true color image, not a photograph, his name would not have been forgotten. He made 3 images of a tartan ribbon with red, green, and blue filters in front of the camera lens. And then he overlaid all 3 to produce a color image of the tartan bow. All 3 were remarkable accomplishments, but it is what he did in a 3-year period from 1858 to 1861 that made him rank with Newton and Einstein. In 1858, 4 equations about electric and magnetic fields were known: the Gauss equation, the Faraday equation, the Coulomb equation, and the Ampere equation. The equations of Gauss and Faraday are sourceless equations. The equations of Coulomb and Ampere have sources: the charge density and the current density. The 4 equations are interconnected, but in 1858, they did not form a single entity. Maxwell's innovation was the addition of a term to the Ampere equation. Today, we call it the displacement current term. How did he arrive at that term? Well, consider a time-varying current flowing in a closed circuit containing a voltage source, a wire, and a capacitor. Now apply Ampere's circuital rule to surface S1 with rim P. S1 is a flat surface. You will get the integral of H dot dl on P to equal the current crossing the surface S1, which is I. Now apply Ampere's circuital rule to surface S2 with rim P. S2 is a cupped surface passing between the plates of the capacitor. You will get the integral of H dot dl on P to equal the current crossing the surface S2. That is 0. The two right sides are different, which violates Stokes' theorem. Maxwell therefore created the idea of a displacement current in the capacitor, and that had to be equal to the current in the wire. The discrepancy vanished, electricity and magnetism were united, and electromagnetics was born. These four equations are now the foundations of numerous modern technologies, from communications to medical diagnostics to materials processing to computing. Between F equals ma and E equals mc squared, their stature is iconic, as attested to by tattoos and t-shirts. Maxwell published a lucid 2-volume textbook on electromagnetics in 1873. A copy once owned by another great physicist, Ernst Mach, is now at the Carnegie Mellon University Library. The first edition probably costs a few $1,000s today, but you can buy a reprint of the third edition from 1891 for just a few dollars. Could Maxwell have foreseen the emergence of nanotechnology? Well, he was a continuum theorist. His equations apply to vacuum and bulk matter. There was no concept of discrete elementary entities such as the atom in his equations, much less the electron and the proton. Though he did initiate the idea of molecular vortexes to explain lines of magnetic force. Two major developments took place after the postulation of the electron. In the first, the Maxwell equations were reformulated by Hendrik Lorentz and Oliver Heaviside for a microscopic perspective in which there are only two fields, lowercase e and lowercase b. Both sources and matter are represented by distributions of point charges Q sub L with velocity V sub L at time-dependent positions R sub L. A spatiotemporal averaging of the fields and sources then brought back the form Maxwell had created, but only the form, not the meaning. The second major development was field quantization. For example, the electric field inside a cube of side L would be expressed as a 4-dimensional sum, in which the wave vector is quantized and the operators A and A dagger obey the boson commutation relations, and similarly for the field lowercase b. Nanotechnology became recognizable only during the 1980s, and its emergence has boosted the popularity of the Maxwell equations so much that for a scientist in any discipline to confess ignorance of the existence of these equations would amount to an admission of illiteracy. Article 314 of Maxwell's treatise contains a hint of nanotechnology. On these 2 pages, he predicted the effective properties of an ensemble of electrically small spheres, which nanospheres are. That Maxwell would have done so is not surprising. His guru was Michael Faraday, who in his 1857 Bakerian lecture had ruminated on the red color of glass containing very fine gold particles, today's nanoparticles. Ruby glass, of course, had been known for centuries. Gold nanoparticles in glass create the vivid red color on transmission. View colloidal gold at 90 degrees to the illuminating light and you will see other colors too. Nanotechnology is concerned with atomic, molecular, and macromolecular phenomena that occur at the nanoscale. The nanoscale is defined in our country as follows. At least one of 3 spatial dimensions must have a characteristic length scale between 1 and 100 nanometers. The British definition goes lower to 0.2 nanometers. At these length scales, bulk matter, like tables, chairs, everything in this room that you can see, these things don't exist. Instead, clusters of atoms and molecules do. The cluster properties are very different from those of bulk matter. The cluster properties are also very different from those of solitary molecules. As such, semi-classical theories are needed to interpret phenomena at the nanoscale. How small is 1 nanometer? As Gizmo complains to Miss Buxley in this cartoon, it is too small to see by the naked eye. Well, Gizmo would need a high-power electron microscope to find a needle of length 1 nanometer. A few years ago, I accompanied my wife to a nutrition supplement store. While waiting for her to buy vitamin C tablets, I picked up a promotional book on a chemical supplement for building up muscles. Guess how did the book promote the product? By the slogan, "Experience the power of nanoparticulation." In Malaysia, I found nano candy. In Italy, one can get a little drunk on Vino Blanco Nano. Nano vodka from Belarus is stronger. In short, nanotechnology today is pervasive and ubiquitous, which makes it difficult to estimate a dollar figure for the nanotech economy. One estimate I found of the global nanotech market is $42.2 billion in 2020, with a fourth in the United States. The global figure is expected to increase by 75% in 2026. It may be better today to speak of nanotechnologies rather than nanotechnology. There are incremental nanotechnologies, primarily using nanoparticles and thin films. Evolutionary nanotechnologies, which are of more recent vintage and are exemplified by quantum dots and carbon nanotubes. And radical nanotechnologies that are not yet clearly in sight. But some consider the appearance of radical nanotechnologies to be imminent. Even movies depicting visions of radical nanotechnologies have been made in the last few years. My favorites are Gattaca and the second version of the Manchurian Candidate with Denzel Washington, not Frank Sinatra. Nanotechnologies involve the engineering of materials. Some types of engineered materials are so different in their properties from other types that they are nowadays called metamaterials, that is, beyond materials. Now, engineers have had an inordinate fondness for composite materials right from the Bronze Age, when they alloyed copper with tin to make bronze. Surveys of materials literatures reveal that until about 1970, most papers reported measurements of electrical properties, mechanical properties, thermal properties, etc. of materials under different ambient conditions. The research front shifted thereafter to a higher level question. I want a material that can respond to an applied voltage or an applied force in such a way under these ambient conditions. Can you find or design a material, composite or otherwise, that will satisfy these requirements? The concept of design of a material for a specific functionality emerged. About the year 2000 came a further shift. So confident did industrial managers become of the prowess of material scientists and chemists that they started posing an even higher level question. I want this device or this structure to operate in such and such way. Figure out first the performance requirements for the materials required, and then design and fabricate those materials. Design for system performance calls for multifunctionality, materials have to be multifunctional. Let me explain multifunctionality with a splendid example described by my Penn State colleague Chuck Pecos. And the example is the fuselage of the Boeing 787 Dreamliner. Now, there are usual mechanical requirements on an aircraft body: lightweight, because you want fuel efficiency; high stiffness, because you don't want the body to deform; and high strength against rupture. For the 787, there were at least two additional requirements that I know of. The first was for a quiet cabin. Therefore, the outer body would have to acoustically isolate the cabin from the wing-mounted engines. The second additional requirement was for a more moist cabin so that fewer passengers would suffer nosebleeds. This called for thermal isolation of the cabin from the external atmosphere so that condensation would not occur in the cabin at high altitudes. Nowadays, conducting and other fibers are embedded in an aircraft body for reinforcement, to serve as antennas, for sensing the environment, for monitoring the structural integrity of the fuselage, and even to morph the body for greater fuel efficiency. The term metamaterials appeared in 1999. Roger Walzer of the University of Texas at Austin coined it. In 2001, he gave a formal definition in a book chapter. Macroscopic composites having a man-made three-dimensional periodic cellular architecture designed to produce an optimized combination, not available in nature, of two or more responses to a specific excitation. I have two issues with this definition. The first is the sexism inherent in the term man-made. The second, how can anyone explore the breadth and depth of nature? We can dispense with both problematic issues and make the definition leaner. Periodic composites designed to produce an optimized combination of two or more responses to specific excitation. So we focus on three attributes of metamaterials: subwavelength scale non-homogeneity, periodicity, and multifunctionality. All three attributes can be realized using the geometric notion of cellularity. Cellularity and multifunctionality are the obverse and the reverse of the same coin, and it is a 24-karat gold coin. Cellularity in structure leads to multifunctionality in performance. How? Think of a machine. It is made of many small components. Each component performs a simple task, but the assembly of components can perform many very complex tasks. A simple example is the Swiss Army knife. A more complex example is the office copier that needs the operator to have at least a PhD. Now, think of fabricating elementary devices that may be classified as elements of different phenomenological types. Some are energy harvesting and energy storage elements. Others are sensor elements. Yet others are communication elements, and so on. Assemble several mutually compatible elements in a cell. Make different types of cells. Now arrange the cells in different formats. In the simplest format, all of the cells are of the same type. You automatically have periodicity then. But more complicated formats are also possible. As an example, different types of cells can be arranged in spatially non-overlapping domains. In each domain, there are cells of only one type. Two different domains have cells of two different types. Thus, there is local or domain-wise periodicity, but overall, the structure is graded functionally. One can even have a fractal metamaterial in which all the cells are identical in constitution but are of different dimensions. Chip Cohen is a pioneer in this area. There is a biomimetic flavor in this conceptualization of metamaterials. A cell can be thought of as analogous to a biological cell. A biological cell has many different organelles, such as mitochondrions, ribosomes, vacuoles, a nucleus with a nucleolus, and so on. Each organelle performs a specific function. Just as masses of different types of biological cells act as multifunctional organs, so can supercellular assemblies serve as multifunctional materials. This vision in electromagnetics is being realized through metasurfaces. A metasurface is a biperiodic arrangement of a planar element on a surface. This repeating element is called a metaatom. These artificial materials have become immensely popular in the last decade. As this graphic shows, there are several classes of metasurfaces, including passive metasurfaces, active metasurfaces, gradient metasurfaces, and so on. These devices are used for controlling the frequency, polarization state, and wavefront. They can be switched between reflection and transmission modes. They can work as tunable and switchable absorbers. They can be designed to cloak as well as to sense. Let me refer to Chip Cohen's work on microwave metasurfaces for cloaking here. Now, this example is of an X-band antenna with a metasurface. And these are X-band polarization converters. We can make multifunctional and multi-controllable metasurfaces by using two or more materials in the metaatom. One material could have thermally affected electromagnetic properties. Another material could have electrically or magnetically or pressure affected electromagnetic properties. The metaatoms can be assembled in diverse arrangements. Singly controllable metasurfaces have been experimentally realized. These can also be bifunctional. Multi-controllable ones have been designed but not yet experimentally demonstrated to my knowledge. Many techniques are available today to fabricate metasurfaces. These include self-assembly, physical vapor deposition, chemical vapor deposition, lithography, and printing. These techniques can also be hybridized. And now I come to the last stop in this talk. Sculpture-thin films with which to exemplify nano-engineered metamaterials. These are assemblies of parallel curved wires whose diameters are on the nanoscale or the submicron scale. The shapes of the nanowires is controllable with the stipulation that the nanowires must grow away from a substrate. Here you see scanning electron microscope images of some sculpture-thin films. The shaped nanowire morphology is clearly evident therein. On the left, you see a sculpture-thin film which is made of nanowires that seem to be shaped like chicken bones. Then in the middle, the nanowires are shaped like C's. And then on the right side, you see nanowires that are shaped like S's. As the nanowire assembly grows, the shape can be changed almost abruptly. Here you see helical nanowires with the pitch changed abruptly almost midway through the sculpture-thin film. The abrupt change in nanowire shape occurs within 3 to 5 nanometers of growth. This is because sculptured thin films comprise the clusters of 1 to 3 nanometers as building blocks. The inter-nanowire as well as the intercluster porosities can be controlled by varying the deposition conditions. Let me go on to chiral sculptured thin films, which are assemblies of nanohelixes. On the top, you see, is a structurally right-handed chiral STF. On the bottom is a structurally left-handed chiral sculptured thin film. Polarized light can also be chiral. Now suppose that circularly polarized light falls normally on a chiral sculptured thin film. If it has the same handedness as the chiral sculptured thin film, then this light will be highly reflected. If the two handednesses are opposite, then the reflectance will be small. This polarization state dependent phenomenon is called the circular Bragg phenomenon, and it occurs in a specific spectral regime. Here you see a blue band in the transmittance spectrum of incident circularly polarized light. The chiral STF is structurally right-handed. The blue band is absent in the transmittance spectrum of incident left circularly polarized light. So the structurally right-handed chiral STF can be used as a band stop filter for right circularly polarized light. The blue band switches if the nanohelices are left-handed. Hence, the structurally left-handed chiral sculptured thin film can be used as a band stop filter for left circularly polarized light. We can take one period left-handed, one period right-handed, then the next period left-handed, and the next period right-handed, and so on. We can now make band stop filters that are independent of the polarization state of the incident light, as you can see by the blue bands, by the very dark blue bands in all four of these transmittance spectrums. An important type of band stop filters is the spectral hole filter. If the center of a chiral sculptured thin film has a 90-degree twist in it, it becomes a spectral hole filter. The Bragg regime is around 50 to 100 nanometers wide, but the spectral hole is around 10 nanometers wide. The spectral hole is a very sharp feature in the spectrum. Now, sculptured thin films are porous. If the void regions of a chiral sculptured thin film with a twist discontinuity, if these are infiltrated with a fluid, the spectral hole will shift. Thus, the device can be used as a fluid concentration sensor. Here you see spectrums for sensing water vapor as the vapor density changes with time. Now, using the Maxwell equations, we can predict the optical properties of a sculptured thin film from a nanoscale model. Then we can use the Maxwell equations again to determine how much of light of a certain color and polarization state will be reflected, transmitted, or absorbed by a sculptured thin film. Hence, all optical experiments can be matched well against theoretical explanations and predictions, but I am not going to show more equations today. A recent development towards multifunctional sculptured thin films is the fabrication of these materials made of parylene C, a polymer approved for human implants by the Food and Drug Administration. My students have used a physicochemical evaporation method to produce a chiral sculptured thin film with a period of about 20 micrometers. This can serve as a band stop filter for circularly polarized electromagnetic waves at about 15 terahertz frequency. The same film can serve as a band-stop filter for circularly polarized waves at 3 gigahertz frequencies, but these waves are not electromagnetic. They are elastodynamic. They are shear waves. So two functionalities, terahertz and ultrasonic, can come out of exactly the same thin film. But that is not all. One of my students evaluated these thin films as interlayer dielectrics for flexible electronics. Then the material can withstand repeated mechanical and electrical loading and unloading. After impregnation with quantum dots, these films can emit visible or ultraviolet light, according to theory. But that is not all either. These films could also function as superhydrophobic impedance matching buffers for photovoltaic solar cells to thereby increase the efficiency. One of my students showed that these films can also function as tissue culture substrates, as well as coatings for either promoting or inhibiting attachments of specific proteins to certain substrates. So just one film can have terahertz, ultrasonic, nanophotonic, electronic, photovoltaic, and biomedical applications. Through just a few examples, I have shown you that the interplay of material type and diversity, macroscopic geometry, and microscopic morphology is a vibrant arena for electromagnetics researchers today. Applications of the Maxwell equations are ever expanding in this era of nanotechnology, metamaterials, 5G and 6G, information technology, neural engineering, etc. I wish that I were 25 years old again. The innovation of James Clerk Maxwell, the displacement current term, was thus an acorn that has engendered many mighty oaks in the forest of knowledge. Yet, neither Scotland nor the United Kingdom has done much to perpetuate the memory of Maxwell. Ignorance of this fine scientist is widespread in Scotland. In March 1995, I was at the University of Glasgow to deliver a lecture. I thought of buying an 1881 biography of Maxwell written by Lewis Campbell and William Garnett, if I could afford the price. Colleagues in the mathematics department of the university directed me to a second-hand bookstore on Great Western Road, past the River Kelvin. I inquired of the salesman if he had a biography of Maxwell. He replied, "Maxwell who?" Even after I said to him that Maxwell was arguably the greatest scientist to ever hail from Scotland, he was not able to recognize the name. Fortunately, in 2008, a statue of Maxwell was installed in Edinburgh. I think that it is the only public statue of Maxwell on this planet. Holding a color wheel, he is sitting on a chair with his dog Toby on the floor. The 4 Maxwell equations are inscribed in a plate embedded in a big pavement surrounding the plinth. Earlier this year, some of us great-grandchildren of Maxwell, intellectually speaking, we gathered in his Edinburgh home for a symposium on theoretical electromagnetics. The address is number 14 India Street. All of us trotted over about 10 blocks to be photographed with his statue in the evening. At the door of Maxwell's house, here you can see me with Maxwell, my grandson. And that's all, folks. I have not exceeded my allocated time, so I'm happy to take questions. Thank you.